In this video, we will be introduced to the components used in our course of study of electricity. Each slide will show a photograph of the component, its name, and the symbol used to represent the component in a schematic diagram. At the end of the video, there will be a short quiz so you can check what you have learned. The first photo shows the familiar wall switch we use to turn lights or other devices on or off. Specifically, it is called an SPST switch, which stands for Single Pole, Single Throw Switch. The diagram for this basic switch is shown on the right side of the slide. When the arrow is in the position shown, the switch will be off and no current can flow. When the arrow is drawn so that the arrow is horizontal, the switch will be on and the current can flow. This next photo shows several multi-pole switches. The one at the left of the photo is a 10PST dual inline package switch. Each of the 10 individual switches can be either on or off and are all independent from one another. The small switch in the center of the photo is an SPDT switch, and the large switch at the right is a DPDT switch. The component diagram shows this double pole, double throw switch. In the diagram, there is a dotted line which indicates that the two poles of the switch are connected together mechanically but not electrically. You can see this mechanical connection in the photograph. It is the plastic handle at the right side of the switch which allows both poles of the switch to be activated by one handle. This slide shows the classic incandescent light bulb with a tungsten filament. These are largely being replaced by fluorescent bulbs, or better still, LED lamps. The newer LEDs give a very nice quality of light, and they're much more energy efficient than incandescent bulbs. The metal base of the clear bulb at the right of the photo is called the Edison screw and is standard for 120-volt lamps. The threaded part of the base is connected to the neutral wire, and the base central pin is connected to the live line wire. The component symbol shown at the right is very easy to recognize as a filament lamp. The LEDs shown in this photograph are mainly used as indicator lights. The rectangular one in the center is a 7-segment LED, which can be lit to show each particular digit from 0 to 9, as well as the decimal point. The symbol for LEDs has a triangular shape which indicates the direction of the current must flow through the LED. So in this orientation of the symbol, the left lead is the positive connection and the right lead is the negative. Note that current flow is from positive to negative, while electron flow is from negative to positive. More about that later. The two small arrows above the symbol represent that light is being emitted by the component. This slide shows a small neon bulb. It consists of a glass envelope with 2 electrodes, and it is filled with neon gas at low pressure, as well as trace elements of other gases. Neon bulbs are often used as indicator lights. The symbol shown at right depicts the 2 electrodes. Notice that there is no filament connecting the electrodes. The electricity flows through the neon gas within the tube. This next slide shows a photo of a number of dry cells. We often refer to them as batteries, but strictly speaking, a battery is made up of more than one cell. All of the cells shown here have a voltage of 1.5 volts when new. The little button cells on the right are alkaline cells made for watches. In the past, these contained mercury, but for environmental reasons, mercury is no longer used in them, or the amount used has been greatly reduced. Note that the positive side of the symbol is the longer line, so it is easy to remember the polarity when looking at a schematic diagram. Here we have what are properly referred to as batteries. The large green battery contains 4 1.5 volt cells connected in series, resulting in a total of 6 volts at the terminals. The 2 9-volt batteries each have 6 small 1.5 volt cells connected in series within the battery case. Note that the symbol for the battery shows several cells and the positive and negative polarity. Usually the schematic diagram will also indicate the total voltage which the battery provides. In complicated schematic diagrams, inevitably some of the wires will cross one another. In that case, it will be necessary to indicate whether the wires are actually connected to one another or whether they are above or below each other and not electrically connected. The symbols for crossing wires clearly show which is the case. In this slide we see two multimeters which can measure current, resistance, and DC or AC voltage. The meter on the left is analog, using a moving coil and needle to indicate the measurements. This type of meter has the advantage of being quite inexpensive. In addition, with the moving needle, it is easy to see how the voltage is changing. The digital meter is more expensive, but it is easier to read the numbers on the large display. The symbol for a meter is a very easy to understand graphic. The antenna shown in this photograph is for over-the-air digital television. Its large surface area and raised height enable it to receive the radio waves from many kilometers away. The symbol shown at right is easy to recognize, and it is usually drawn protruding from the top of schematic diagrams. At the left side of this photo is a 1 ohm 10 watt fixed resistor. It is classified as a power resistor because its large size and ceramic casing allow it to dissipate the heat generated when current passes through it. The two resistors on the right are carbon composition resistors. They conduct the current through a channel filled with a carbon and clay mixture encased in a plastic coating. The resistance value is the ratio of carbon to clay used, and the power rating is dependent on the overall size of the case. This type of resistor ranges from 1/8 of a watt to 1 watt. The symbol for resistance is the sawtooth line shown at right. The next slide shows 3 potentiometers, also known as pots, or more descriptively, variable resistors. They usually have 3 leads connected to them. The center lead is the wiper, which moves along the resistive element as the knob is rotated. The other 2 leads are connected to the ends of the resistive element. Typically, these variable resistors are used for the volume control of radios and television sets, or for tone control adjustment. The symbol for this component is the same as the one for the fixed resistor, except for the extra arrow, which represents the moving wiper connection. The next 2 slides have several questions which you should try to answer to make sure that you have learned what you have been taught in this short video.